Okay, perfect. Okay, welcome everybody to the MCRN colloquium, returning after a little 2-week break. My pleasure today to introduce Dr. Rohit Khandelwal. He got his PhD at the Indian Institute of Technology in Delhi, India in 2022. And right now he's a postdoctoral research fellow beginning in August 2023 at the Center of Mathematics and Artificial Intelligence at George Mason University. He's working on optimization problems governed by nonlinear partial differential equations with Professor Raviart Antil. And so looking very much forward to your talk today, and he'll be talking about variational problems with gradient constraints, a priori and a posteriori error identities. So with that, please take it away, Rohit.
Yeah. Good morning, everyone, and thank you so much, Christian, for this nice introduction. And sincerely, thank you so much, Emmanuel and Christian, again, for giving me this great opportunity. So the title of my today's talk is Variational Problems with Gradient Constraints, A priori and a posteriori error identities. So this is a joint work with my postdoc advisor, Professor Raviart Antil, and Professor Soren Bartels from University of Freiburg, and Dr. Alex Kantelbach. He's a postdoc at TU Berlin. And we would also like to thank the funding agencies for the partial support. So this will be a quick outline of my talk today. So I'll briefly start with a nice motivation, and then I'll try to justify or show you the main or the key idea for the standard Poisson equation. It's a 2D elliptic partial differential equation. And from there on, we'll try to introduce some key ingredients. So the first will be the Fenchel conjugate. So it comes in the convex analysis theory. And I'll briefly describe there some examples as well. And then we'll state our main problem, which will be like variational problems having the gradient constraints. And therein, we'll try to formulate our problem. We'll introduce the primal and the dual problems respectively. And later on, we'll describe what are the optimality conditions there and try to derive the posteriori error identity at the continuous level. At the continuous level means that there is still not being discretization in the role. And then to justify our results in the discrete sense, we'll try to define some finite element function spaces, which will be Crouzeix Raviart for the primal problem and the Raviart for the dual problem. So these two are quite standard in the mixed methods, and they both are basically dual counterparts of each other. And I'll describe what do you mean by the dual counterparts later in my slides as well. And then we'll try to do it again on the discrete level as well. We'll try to define the discrete primal and the dual problems respectively, and derive some discrete optimality conditions and try to validate our results, which is a posteriori error identity at the discrete level as well. And lastly, this is crucial that we'll end our results by showing some convergence rates as well, which are a priori error estimates. And lastly, we'll show the algorithm which we have used to basically validate our theoretical findings. And it's a still ongoing work, but we do have some preliminary numerical results to show. All right, so the motivation is that, so the approach which we have used is quite simple, is quite identical, and it can be applied to various problems in the fields of structural engineering or optimal finance, and even in linear elasticity models as well. For example, these all problems which I've shown you here are all non-smooth optimization problems, or you can say that non-smooth variational problems. So the first is we are trying to minimize this energy functional IU, where U satisfies basically IU is this, and G is any noisy image. So it's a famous model given by Rudin, Oshner, and Fatemi. And you can see that there is a total variational norm present here. So due to that, it's a non-smooth problem. And you can simply apply our approach to this problem as well. And then there is a famous problem in the linear elasticity or in the mathematical finance, which is the obstacle problem. So you can assume that there is a circular membrane which is lying above a rigid plate at a distance of psi, and a wire hanging onto the membrane, and it's horizontal in direction. So what will happen if we load the force onto the vertical direction onto the membrane? It undergoes deflection, and we might get a contact area between the plate and the membrane. So the boundary of that contact set or the coincidence set is basically unknown, and it's called the free boundary. And this obstacle problem is basically the free boundary problem. And it has various applications. For example, in mathematical finance, this free boundary basically distinguish the two sets which are the basically optimizing region and non-optimizing region, where you can really optimize your options, and where you don't want to optimize, you can really sit down and wait. So in this, we are trying to minimize this energy functional, and you can see that this constraint, where for simplicity, we assume that my obstacle is 0 here, and where we have put the obstacle in the indicator functional setting. So it's a positive indicator function. It takes the value 0 if this constraint is satisfied, and it takes the value plus infinity if it is not. And the other example where you can really apply our approach is the following Signaroni contact problem. And it's very famous in the linear elasticity models. So the difference between the obstacle and the Signaroni problem is simple. The contact between the obstacle and the displacement is inside the domain omega in the obstacle problem, whereas in the Signaroni problem, it's on the part of the boundary, where we denote by gamma c, which we call as contact boundary. And you can see that we put the constraints again in the indicator functional setting. And again, it's a non-smooth problem because indicator functionals are non-differentiable functions. But for this talk, we are really interested in this elastoplastic torsion model. So suppose you have a long infinite cylinder and you twist it from top and the bottom. So what will happen if you leave the twisting? There will be a torsion which will form at the top of this surface. So you can really model this problem into the following mathematical setting, that we are trying to minimize this energy, but we have put the constraints in the gradients now. So we are trying to put the constraints in the modulus value of the gradients. So it has been looked previously in the literature, this problem, but we'll try to mention where are the drawbacks and where are the loopholes in the past. And we are really modifying those results. All right, so let's quickly look at the very simple Poisson problem. I'll try to give you a main idea here, and please try to ask in between any doubts if you have. I'll be very happy to discuss more during the talk as well. So let us consider omega to be any bounded simplicial Lipschitz domain, and where the boundary is divided into two disjoint boundaries, Dirichlet and the Neumann. And I hope everyone is familiar with this problem. Minus Laplacian u is equals to f, and these are the boundary conditions. And it has various applications, like in thermal heat as well. You can model this problem. And for example, we have shown that there is a membrane deformation as you applied the force in the vertical direction. So you can see the deformation in the displacement. But so this problem here is the strong form because it needs more regularity on the solution here. But you can really multiply this first equation with the nice test function or the smooth functions, And you can really use some Green's identity, and you can derive this nice weak formulation. And you can use the nice Rees representation theorem, or you can use Lax-Milgram lemma to prove the existence and uniqueness of this problem. All right, so if we have the weak problem, so we can always, so sometimes people really are interested in the stress variable as well. So for that, we introduce this new auxiliary variable z and try to introduce the mixed problem. So here the unknowns are both stress and the displacement. The z is the stress variable and u is the displacement. And now z comes from this nice vector valued space, which we called as divergent space. And if you introduce this auxiliary variable and you do some integration by parts, you'll get this first equation. This is nothing but the minus Laplacian u is equals to f. And this is the proper weak formulation. We are doing nothing but just multiplying these two equations and doing some integration by parts. So we are really interested in the mixed problem. And let us try to see another equivalent variational formulation for the standard Poisson equation. So the primal problem is as follows, that we are trying to minimize this energy I, which is defined on the primal space. Please note that it's a scalar valued space, and the energy is as the following. So it's a nice, smooth, quadratic energy, and you can really try to evaluate its first variation, and you can get your primal problem back. So we just introduce this phi variable here, which is equal to this, and psi is equal to this. And we know by direct method of calculus of variation that you can really show this I is coercive, it's weakly lowered semi-continuous, and you can show that the minimizer exists. And for the dual problem, it's nothing but to maximize the d energy functional, which is again defined on the dual space, which is again the vector valued space, which is introduced as following. Please note that we are putting the divergence constraints in the indicator functional setting. If you remember, if you allow me to go back, we have a constraint here, divergence z is equals to minus f. So we put this constraint in this via indicator function. And again, you can use direct method of calculus of variation to show the maximizer exists and it's unique as well. So now the key idea is the following, that you can use strong duality results, which are already established in the literature. You can use standard convex analysis arguments to show that the both energies coincide at their respective minimizer and the maximizer. So there exists a unique maximizer which lives in this dual space such that these are equal. And you can also show that it's one-to-one relation with the following optimality conditions. But we are interested in this Prager and Sainz result, which was given in back 1947. So suppose let U and Z solves our primal and the dual problems respectively, and V and Y are any arbitrary elements, then we have the following kind of error identity. So what's it saying? It's saying that you can really bound the primal error plus the dual error with this new gap estimator, which we denote by eta gap. Please note that it's nothing but the difference in the energies in the primal and the dual problems. And the important point here is that we are getting the equality, and here V and Y are any arbitrary elements. So I want to highlight that this step is independent of the discretization. You can use any discretization you want, and you can evaluate the right-hand side and justify your results. So that's the first advantage. And the proof is quite simple. It just uses Pythagoras theorem. You can show that y minus z is orthogonal to gradient v minus gradient u. And that's it. If you have the Pythagoras, then this result is quite immediate. And the second is the estimate given by Micklin in 1964, which really gives kind of a posteriori error estimator for only the primal problem. But the proof uses the standard convex duality arguments like weak duality and weakly lower semi-continuous of energy I, which is the primal energy. And it's saying that you can bound the difference in the, you can bound the primal error with this gap estimator. And again, this V and Y are any arbitrary, so you can choose and you can try to evaluate in the discretization. All right, so the goal of our analysis of my talk to derive these same kind of error identities first at the continuous level, and then via nice finite element discretization will prove at the discrete level as well. All right, so these are the goals. And here I want just to highlight that our constraints are the following, and where this zeta is any arbitrary L infinity function. So our problem is.
Can I ask a question about the previous slide?
Yes, sure. Sure, John.
I was really curious about the right-hand side. So just if I naively look at this theorem, if I just set the right-hand side equal to 0, just like pick delta V equals Y, right? Doesn't that tell me that V and Y are then optimum? Like it seems like it's magic.
Yes, they are optimal. But I think that will hold only at the U and the Z, which are unique maximizer and the minimizer respectively. Otherwise, the right-hand side won't be 0.
But you have total freedom on V and Y, right?
Yes.
Oh, I see. But that won't tell you then that V and Y are
satisfy
good
the
of the two different optimization problems.
Yeah.
You just know. I see. I understand.
Yeah.
Sorry about
yeah, you have a point. Those V and Y, which will make this right-hand side 0, can satisfy two different problems.
That's right. Yeah.
Okay. All right. So thank you so much. Yeah. So we have considered this problem in the full journal setting. And what do you mean by journal? That our obstacle zeta is any arbitrary L infinity function. So the critical point here is that all the steps I have already mentioned in the outline, but please note that in our opinion, the key step is to choose primal space and the dual space. If those two spaces are correct, then I hope the analysis will be okay. But if you start with the wrong primal space, then you end up with the wrong dual space, and then everything will be messed up. So in our problem, we'll show you what space we choose later on. Let's collect quick tools, which I'll be using later on quite frequently. So this all comes in the convex analysis theory. If let phi be any Lebesgue measurable function, then the Fenchel conjugate is defined as the following. So from the graph, you can see that if phi is any this Brown mapped function, then this minus of this guy is nothing but the value of the tangent at t equal to 0. Basically, it's the value of the tangent at t equal to 0, the minus of this guy. And suppose if phi is not differentiable, then you can ask me that how will you compute the value of the tangent? So then you can really see the minimum of all such values. So there will be many tangents then. So just took the minimum of the values and see the y-intercept. And we have the famous Fenchel-Young's inequality that if you have phi and the phi star, that will satisfy this nice inequality. And for example, if you have this f, which is mod x to the power p divided by p for any p in this range, then its Fenchel conjugate is equal to this, where p dash is nothing but the conjugate exponent of p. You can use this definition to evaluate this guy. It's just 2-3 lines. And for example, if f is the positive indicator function, you can try to evaluate f star and you'll end up in the negative indicator function. All right, so if you are okay with this, let's move towards our main problem. So as I have earlier mentioned that we have considered in full journal setting, which means that our f is any L1 function. We are not putting any constraints on f. We are not putting any constraints on the zeta as well. And we have started with W0, 1 infinity function space, which is nothing but the functions are in L infinity and the first distributional derivative is in L infinity. Why? Because we try to put the constraints in the modulus value of the gradients. So the gradient, this constraints almost holds almost everywhere in omega in the pointwise setting. So we thought that initially we have to start with the space. So this should be the correct primal space to begin with. And we can introduce this indicator function on the vector valued function spaces. And if you try to see this composition with this guy and the gradient, we introduce this ik, which is now on the primal space, by the way. And we can define this, our primal problem, using this ik and this k set as follows, that we are trying to minimize this I energy, which is defined on the primal space, which is equal to this. We are doing nothing here. We are simply following what we have in the Poisson equation, but we are trying to put the constraints on the gradients here. This ik is the composition, so the gradients will come into the picture. But now please note that this phi is the sum of the first two guys. And as I earlier mentioned, this indicator function is non-differentiable. So this is a non-smooth minimization problem. But you can still use the direct method of calculus of variation to justify this problem has unique solution. But this phi will be important. Please remember this phi. All right, so let's quickly review the literature survey. So people have looked into the past, this problem in 2009, these authors, they consider the same problem, but they started with W012. And in our opinion, this is an incorrect space to begin with. So hence their dual formulation is also incorrect in some sense. They are not capturing the properties of the dual variable correctly. And I'll show you how. And later on, more recently, Professor Franz Schuli and his collaborators, they are focusing on this problem, but they are putting some constraints, like they are putting some, like f and zeta are constants. And please note that if f is a constant, this problem is nothing but the obstacle problem. You can convert this problem into the obstacle problem.
I have
And
a question. Sorry.
Yes, Emmanuel.
Is that okay? Unless you
Yes.
want to.
No,
So
sure.
in the previous slide, right?
Yes.
So when you have the constraint, so this subscript in the K, is it related to the constraint? Because your constraint was the gradient of U is bounded.
Yes.
Right?
Yes.
So then this subscript that you have here for K.
This one?
No, the previous one. Okay,
This
yes.
one?
Yes. So when you do it, this is related to the constraint that you're in.
Yes, because this y is a vector valued function. So what does this mean? This means that if the constraint is satisfied, it takes the value 0.
Mm-hmm.
And otherwise it's infinity.
Got it. Okay. Thank you.
But we put the ik here, which is the composition. Anyway, yeah, that's it. So Professor Franz Schuli and his collaborators, they are putting some constraints, at least in the first two papers, which, what do you mean by constraints? Like they are playing with nice f and zeta to be constants, and the analysis is pretty easy because the problem is obstacle and everything is, there is a vast literature available for the obstacle problem nowadays. But more recently, these guys put a paper on arXiv where they have taken into the consideration with the non-smooth source term, which is non-constant source term, but still they didn't answer the main question, the how to prove the convergence rates. So we are really trying to fill these gaps as much as we realize that there are in the literature. All right, so if you remember, this is the phi. Sorry, I'm going back and forth here. So if you recall this phi, and if you use the definition, which I showed you, the supremum definition of the phi star, you can really evaluate, and you can see that it's nothing but, the phi star is nothing but the Huber functional. And this Huber functional comes in the optimal finance setting quite a bit. If you can see that for the smaller values of S, it's a quadratic function, and for larger values of S, it's a linear function. And now we are really thankful to this reference 9, which is a paper by Professor Tolland, because we need a dual space. We need a isoparametric dual space for the L infinity. And we found it, the precise definition in this paper. And this is the space which we denote by BA omega. So please note that these are vector valued, bounded and finitely additive vector measures. Everything is in measure setting here. So I'll not go into the details, but this is the nice decomposition which he showed in his paper, that every vector measure mu can be decomposed into the nice regular y function. So y is irregular, it's in L1, and the mu_s is the singular part of the mu, which again lies in this dual space. And we have the orthogonality as well. And I will relate to the Poisson problem as well soon. So if you try to derive the dual problem, it's nothing but we are trying to maximize the d energy function, which is defined on the dual space now, which is equal to this. And k star is the following. So if you think that everything is smooth here, there is no singular part, and we boil down to the Poisson equation case, you can try to do the integration by parts here. If you throw the derivative onto the nu, you will get the minus divergence of the nu is equals to f. If you remember, we have the constraint in the Poisson equation in the mixed problem. The divergence of the z is equals to minus f. So we can always go back if we have some smoothness here. But due to this constraint, we have the non-smooth because we have the indicator function here. All right, so suppose we have the dual and the primal problem. So we derived these main results here. So first result talks about the existence of the dual problem, that there exists a maximizer mu, which has this nice decomposition such that the admissibility condition holds. So this is a kind of a constraints in the dual problem. And then using the standard famous celebrated Fenchel duality theorem, we prove that the respective energies coincide at their minimizer and the maximizer respectively. And this weak duality always holds. This holds by the definition of the I and the D. And these are the optimality conditions. So the first optimality condition corresponds to the regular part, Z, which lies in the L1 space. And the second optimality conditions refers to the non-singular, singular part. So these optimality conditions is really telling you that if you have one solution, either primal or dual, you can really evaluate the corresponding solution. All right, so let's now try to derive the gap estimator, because we have to show the a posteriori error identity at the continuous level. So the definition is straightforward. It's similar what we have at the Poisson equation case. It's nothing but the difference between the energies. And we have proved that this eta gap has the following decomposition, where eta gap A refers to the optimality condition A, and eta gap B refers to the optimality conditions B. So I am referring optimality condition A to the regular and B to the singular part. And the proof is quite straightforward. If you start with the definition and you just put the definition of the A, I, and the D here, then you can use the admissibility condition, because we have the admissibility condition to replace this guy and then use the decomposition, and you end up with this. And the first three terms are here eta gap A, and the last two terms are here eta gap B. And now here is our first main result, that a posteriori error identity holds at the continuous level. So this is the total error, which is nothing but the energy, sum of the energies and the primal and the dual problems respectively. And we have proved this, that the total error is exactly equal to the gap estimator. Please note that V and nu are here arbitrary elements, which belongs to this admissible space. So the proof of the idea is really straightforward. It's just two-line proofs. If you start with the total error definition, and if you replace this guy by so these are nothing but the total errors in the primal and the dual problems. It's nothing but IV minus IU plus d mu minus d nu. And you have the strong duality now. So strong duality results is quite useful because these two guys are equal, d nu and IU. So you end up with this, and this is nothing but your gap estimator. So it's saying that the posteriori error identity holds with constant 1. So strong duality is, I should say, is quite crucial for our error analysis. And now I'll try to go quickly here because everything we are trying to justify now at the discrete level, trying to show the same results. So for that, we have choose this Crouzeix-Raviart finite element space. So if in the audience, if they are not familiar with what are finite elements or the Crouzeix-Raviart, I can try to spend a minute or so here. So it's defined via this space. So here tau h is the triangulation, which is the union of the triangles or the quadrilaterals, depending on the domain. So it's the collection of all discrete functions in this space. So you just put k equal to 1 here. And we are putting the constraints in this way. So what they are really telling you that on each edges, if you try to see the integral, the jumps are 0. And what do you mean by this? So if this is a linear polynomial, because k is 1, so it's a piecewise linear polynomial in every triangle. So you can really use midpoint rule here, because midpoint rule is exact in 2 dimensions at least. And you can see that it's nothing but the evaluation of the jump at the midpoints is 0, which means that the function is continuous at the midpoints, that the value of the function from this triangle and from this triangle are both equal at the midpoint. But it won't guarantee you that it will be fully continuous, because you need 2 degrees of the freedom on a line for a linear polynomial in 2 dimensions to justify it's continuous on the full edge. So it's not continuous on the full edge, but it's continuous only on the edges. So these red dots are precisely its degrees of the freedom. That's why we have written its non-conformity, because they are not globally continuous functions, but they are continuous only at the midpoints. And for the dual discretization, we have choose the Raviart vector fields. So their crucial property is that their normal components is constant along every edges, and their jump is also 0. The normal components doesn't have any jump. And I'll try to justify why they are the dual counterparts of each other, as I have mentioned in the outline. So what do you mean by that? If you try to see this nice integration by parts formula, so start with some Crouzeix-Raviart finite element function and start with some Raviart vector field and try to see this nice, left-hand side term. If you throw this divergence and try to use some integration by parts, if you throw this divergence onto the VH, you'll get the first term. And due to the non-continuity, you'll get this nice boundary value term with the jump here. But please note that YH.NS is a constant. So it will come out from this integral. And then the integral on the edges of this guy is 0 due to their property. So there is no boundary integral here. And hence this integration by part holds for any Crouzeix-Raviart function and for every Raviart vector field YH. All right, so this pi h is nothing but the L2 projections. So they are the piecewise constants. So I'm just replacing this YH because I have to use something piecewise constant here. So I'm replacing with this pi h YH. It's a piecewise constant. All right, so this duality connection, which we'll be using later on. So let's define our discrete primal problem and the discrete dual problem. So we are trying to minimize. So we used Crouzeix-Raviart here. So this CR denotes Crouzeix-Raviart. And this is the Dirichlet-Crouzeix-Raviart space. And this is the following energy. And you can note that this we can also define this nice discretization of our closed and convex set K, which is equal to the following. So we are trying to put the constraints and again in the gradient, but at the discrete level. But still, the direct method of calculus of variation holds here, and you can prove that the unique minimizer exists. And the dual problem is similar, that we are trying to maximize this DHRT, which is defined on the vector fields, Raviart vector fields, is equal to this. All right, so we proved similar main results at the discrete level, that there exists a unique discrete maximizer such that which satisfies this nice admissibility condition. Please note that here is no singular part of the dual variable y because there is no measure at the discrete level. So that part is 0. That's why we only get the regular part here at the discrete level. And again, the strong duality result holds that the energies at the discrete level coincide at their minimizer and the maximizer respectively. And likewise, we do derive this discrete optimality condition. But please note that this discrete reconstruction formula or Marini's formula is quite useful. Please note that if you have one, so this UHCR is the primal solution and ZHRT is the discrete dual solution. And this formula will play a crucial role in our algorithm because we try to justify later on that our algorithm is not costly, that we are not solving both the problems. We will only solve the more smooth problem or the more easy problem to compute, and then we'll use this formula and compute the other variable. So that's why this Marini's or the inverse Marini's formula are very useful. All right, so let us introduce our discrete primal dual gap estimator. So which is again the difference between the discrete energies. And here there is no singular part. So this is only the formulation of the discrete primal dual gap estimator. And please note that we can really evaluate this now in our mesh. This is total computable quantity. And the proof is again very easy. You can just start with the definition of the IHCR and DHRT and use the admissibility condition here, and you will derive with this. And we also proved because we have the strong duality at the discrete level, so we can get this a posteriori error identity at the discrete level with constant 1. That the total error at the discrete level is exactly equal to this gap estimator. And in our algorithm, we will compute this guy and we'll show that it's optimal. All right, so let's quickly end up our theoretical results by showing some convergence rates, some a priori error results. For that, we use this nice, very standard quasi-interpolation operators. And we have derived this main result, which is nothing but the total error at the interpolation level can be bounded by this guy, where D is the dimension of the domain. And please note that you can add and subtract here pi h of Z, and you can get this fractional order error rate. So this nu is kind of a fractional regularity of the dual variable. So this was quite new in our error analysis. Nobody has talked about it before in a full journal setting. And now with this, we'll show quickly the idea of the proof. So the idea is very straightforward because we have this nice representation of our total error at the discrete level because it was equal to the gap estimator. So this was our gap estimator. And then you can use the standard Jensen's inequality, optimality conditions, and the convexity, and you can derive this main result. You can prove it. All right, so let us now try to show some algorithm and some preliminary results. Okay, so the idea is that in our algorithm, there are two loops. So the outer loop, so as I have earlier mentioned that the results holds at the continuous level, and those are independent of the discretization. So you can use any method you want, like reduced order modeling or adaptive mesh refinement, or some other methods as well. But for our in our setting, we choose adaptive mesh refinement, which will make sure this gap estimator should go to 0 as you keep on refining your mesh. That means, in other words, as your H will decrease, this gap estimator should go to 0. But in our inner loop, we'll solve the dual problem. And then will use the discrete reconstruction formula to compute the primal solution. So we are really not solving both the problems. So in that sense, it's less computationally costly as well. So we have used the semi-implicit discretized L2 gradient flow to compute the discrete dual variable. And then we'll try to post-process these two discrete solutions and try to estimate this guy. And if this guy is less than or equals to some given tolerance, we'll stop. Otherwise, we'll move with the mark and the refine, which are the standard steps in the adaptive mesh refinement. And after that, we'll again go with the solve method. And likewise, we'll keep on doing it. All right, so this is the first example which we have considered. So it has been taken in the book by Professor Roland Glonsky. So our omega is this is kind of a disk in R2 with center 0 and radius r. So there is no Neumann data here, and f is a constant in this example. And the Dirichlet data is also 0, but our obstacle is 1. And we do have the exact representation of the primal solution, that it's equal to this. Please note that C is the load vector here. And the primal problem here is non-smooth. Hence, we try to use the optimality conditions to evaluate the dual solution. So dual solution was not given before. We evaluate the dual solution and we end up in this nice formulation. And you can note that it's nothing but a it's nothing but a linear vector valued function. And with this nice regularity, so nu is 1 here. And we expect, at least theoretically, we should get order 2 convergence rate. And we try to show it here in this plots. So this plot is nothing but a log-log plot. So we have put the number of the degrees of the freedom on the x-axis and the error on the y-axis. And we have seen that it's converging with an optimal rate. And this constant, we have plotted with different constants like c equals to 2.5, 5, 7.5, and 10. So in every case, we have shown that the total error is exactly equal to, it's basically they are coinciding with one another, the gap estimator at each of the HIs. So this validates our theoretical findings, which we proved in the a priori error bounds. And these are the plots which we have plotted. So the first one is nothing but the kind of a we have trying to show the constraints where the constraints are satisfying. So the red dots here is precisely the contact set, because if you recall here, here obstacle is 1. So the gradient value in the modulus of the gradient value is exactly equal to 1 in the red dots. and it keeps on decreasing. And for the dual variable, here is the contact set that the constraints satisfy equal to 1, exactly equal to 1 here on the red dots. And it keeps on increasing. So this was very cool to visualize, actually. And we are still, it's an ongoing work. We are still trying to, cook up nice interpolation guy, which can keep this gradient preserved, and trying to justify our primal-dual gap estimator as well, via a posteriori error identity. So it's an ongoing work right now. So these are the conclusions. Again, we have started with the non-smooth variational problem, having gradient constraints. We cook up a nice, simple identical tool, and we have introduced our continuous problem, and then the discrete problem, and then we justify via algorithm as well, that how it's computationally less costly. And we have mentioned that we are trying to fill in the gaps which were there in the literature. And we have also recently put this paper on the archive. If anybody is interested, they can go there, and I'll be happy to discuss more. So these are the references which I've used. And thank you so much again for this great opportunity, Emmanuel and Christian. And if anyone has any questions and comments, I'll be happy to answer those.
Okay, great. Thank you, Rohit. Yeah, let's all thank our speaker. And it was a really interesting talk, actually. So yeah, if anybody has any questions, please feel free to ask.
Can you guys hear me?
Oh, yep.
If anybody, I have questions, but unless somebody wants to ask first. Okay, so I'll go ahead with my question. So the first question is, in your epsilon stop, what is the typical value that you use to do that, to plug in for you to stop your algorithm?
Something small, like 10 to the power -3, -4 would be okay to begin with, because we want our
high. You don't think that's a little bit high?
It's high, but I think that's why I said it's nice to begin with and see the behavior of this gap estimator. Is this guy going to 0 or not? And then we can really increase, decrease that value up to 10 to the power -7.
Okay. So usually we go for like machine precision, like 10 to the -15 or something, right? So yours you can't decrease it to that value, because
we have not tried for that smaller values, actually, at least for this example. I think we worked with 10 to the power -6 or 5, honestly. But yes, we can definitely try to see if we start with 10 to the power -14. I think the algorithm will be it will keep on going. It will run for many long hours. Oh.
Okay, so of another question. For your discrete primal-dual gap estimator, right?
Yes.
So you're assuming strong duality, right?
Yes.
But it depends on H, right? Because when you have strong duality, things should cancel out, right? So there's a dependence on the H that you pick as well. So there's a formula that you have when you look at the eta squared gap H. There you go. That's it, yeah. The very one at the top here.
Yeah.
So I'm just trying to understand.
I'm
just trying to understand, like when you assume strong duality, right? So you have that, for example, you have your non-smooth primal solution and you have your dual solution, right? And you're looking at those two. So so I'm just trying to understand the idea behind this gap estimator, right?
So
and dependence on H as well.
So the gap estimator is the following, and you can see that it depends on the h, because this pi h is a L2 projection. So it takes any function and it maps to its integral values. So it's a piecewise constant. So you can really evaluate these all guys which are there, because this VH is any arbitrary function, and this YH is any arbitrary vector valued vector field. So if you have this nice a posteriori error identity, which we proved via discrete strong duality, and you can really try to plot this guy now, and you can see that whether they are equal or not.
I see. Okay.
We try to plot this right hand side actually.
I see. So I mean, so yeah, I mean, so that answered my question, because I had a follow-up question on the proof that you had in this for the strong duality, like in slide 20, right? So I think that is slide 20. Yeah. So that answered my question.
Yeah.
Right.
So here the key idea is that everything now depends on any arbitrary functions. That's why we just remove this u and the nu, which were the solutions.
Okay. The last question.
Sure, Emmanuel.
I mean, so which particular problem that you have used this for? Like any applications, like, or besides what you showed me for your particular example for your solution, that's non-smooth, or did you try to apply it to any problems?
Yes, actually, we right now we are working on a time-dependent obstacle problem. So the time-dependent obstacle, and we are trying to prove similar results for that. And time-dependent obstacle problem has direct application for the pricing of American options problem. So you can really model that problem into the pricing of American options, where the options payoffs plays the role of the obstacle. And we also have some preliminary numerical results there as well. And we'll try to plot the free boundary, which will really distinguish the exercise region and the non-exercise region in the time-dependent case. But there, to prove the strong duality, it's not so easy. We are working on that right now. It's a work in progress.
Yeah, I mean, thank you again for this very nice talk. Okay, it was very nice. Thank you so much.
Yeah, you're welcome. Thank you for pointing out some nice comments and questions.
Any other questions for Rohit? I had kind of just sort of a more heuristic general one. So this gap estimator, I wonder if, because I think a lot in the context of data assimilation, and one thing I'm really interested in is feature alignment. So for example, like if it's sea ice, maybe cracks in sea ice, or the center of a hurricane or something, when we have observations and we do an assimilation, that rather than just adjust values in the field, we move some of these values, right? If your hurricane's close, you just want to shift it rather than have to add all these things, right? So do you think that there's some way that this concept could be formulated so that you could use this gap estimator as a
I was wondering that the problem you mentioned, or the application which you mentioned, whether it can be, I'm not asking, I mean, I'm just thinking about it, that whether we can formulate that problem into a free boundary problem, so that we can form a free boundary between the points where we do see some effect which you want to capture, and if you don't see the effect, if we can form the free boundary problem, then certainly we can apply the approach here, the approach which we showed here.
Okay. Yeah, I'd have to think about it. Yeah.
But it's not in my top of the head right now, honestly.
Oh, yeah, of course. Yeah, it's a very general question for sure. Okay.
But yes, that was interesting question.
Yeah, thanks. Yeah. Be interesting to think about this in terms of free boundary problems, to be honest, because it's always fun to find, I don't know, more correspondences between these very applied things and sort of deeper mathematics, I think. Okay. Okay, any other questions? Okay, yeah, if not, then let's thank Rohit again for a very interesting talk. And yeah, we will have a talk next week, I believe, as well, and we'll see you all then. So
Thank
thanks.
you. Have a good day.
You too.